Following straight on from previous session, you remember me talking that if you form an integral of the form integral spherical harmonic operator spherical harmonic by the volume of some sort, then you may end up needing a kind of matrix of matrices, because you have four parameters in that, what gets integrated, the integrand, the thing that is integrated, because the first spherical harmonic has its two parameters, L and M, and then an operator, and then the second spherical harmonic will have its two parameters, L dashed and M dashed, and then the volume or whatever. So here, for example, I've written out, and I've called this integral, what do I call it? Plus circle. Right? It's just this. So here's your spherical harmonic, conjugated, the usual thing for an integral, and here's your operator A. Now let's assume this operator A hat in this context is one of your AngularMmntm operators, because what this whole chapter is all about. So it would be either L squared or LZ, right? Okay. D, was it capital sigma, is a solid angle, let's say, of this form, right? But conceptually, you've got these four labels, so it makes like it depends where you're putting the emphasis. Like here, where your eigenfunctions here are fairly straightforward, involving just one parameter, it's easy to translate from the operator, talking about operators, to talking about matrices. Right? Because a matrix is just a two-dimensional array of numbers. That's what a matrix is, right? So this would just be one element of a, let's say, big N times big N matrix. But here it's not so obvious. Now with these wave functions here, you can represent. Now, okay, leading into the notion of representation, to represent. So now in group theory, representation of groups is extremely important, and I will be taking you, if you follow the pure math courses I'll be giving M1, M2 at least, so at least two graduate level courses on representation of groups. And you can bring group theory into quantum mechanics, and that's certainly been done. So what is a representation? Well, I'll keep it fairly simple. Let's talk. The most common form is to take a matrix representation of a group. Well, in this case, it's an operator. Now, you could have a set of operators that forms a mathematical group. So, generally speaking, a representation is. I'm just wondering how to say this without getting very technical and very pure math-like. If this were a first year, if it were an M1 group theory course on representation theory, then I'd just throw all the technical terms at you. But I can't do that in a quantum mechanics course at undergrad level. Think of, for each operator, there's a matrix, corresponding matrix, and the algebra, the properties of the operators, for example, the commutator of this set of operators, they will have the same kind of logic, structure, behavior as the equivalent set of matrices. So if you, for example, you form the commutator of two operators A and B, so that would be a hat b hat minus b hat a hat. Well, the result of that result would be equivalent to doing the same thing with the equivalent matrices. So you'd have like matrix A times matrix B minus matrix B times matrix A, and you get a result that's the matrix equivalent of doing the same thing with operators. But I hope that's a long-winded verbal way of. Well, if you have done some pure math, a matrix representation then is, and this is using the technical meaning, is what's called a homomorphism. So it's a many-to-one mapping of the matrices to the operators. And if you don't know what I'm talking about, don't worry. It's this sort of graduate level pure math. But representation theory can be used very powerfully, and has been, in quantum mechanics. So here we have a fairly simple representation, matrix representation of this operator. So for this operator, we get an equivalent matrix just by doing this, by forming this integral. Okay? And this matrix, well, this is just one element of the matrix, but the whole matrix, all big N squared elements like this, that matrix has similar properties to this operator. And you can do the same kind of math with the matrices as you can with the operators. Right? The two, no, they're called algebras, if you like. The two algebras, the two ways of manipulating the operators or manipulating the matrices, they're equivalent to each other. They're like two languages that you can translate back and forth between. Right? One uses the languages of matrices, and the other one uses the language of operators. Now, interestingly, so look upon this now as a representation of this operator. Like this is a fairly simple matrix representation of this operator. Okay? But now look at this one. This is a more complex representation of this operator, because now we're using spherical harmonics with 4 parameters. Here we only have 2. Okay? So in a manner of speaking, by analogy, you can look upon this as a representation of this operator here in the form of a matrix of matrices. Okay? Because you've got 4 parameters, where each element of the matrix is itself a matrix. Alright? Well, if you're not following this too well, don't worry too much. But the reason I'm giving it is it's a lead-in to spin, the mathematics of spin. Okay, so now, so for this here, this integral, you have 4 parameters, right? L, M, L dash, M dash. Now, for your operators, A hat, if they are angular momentum operators, L squared or LZ, then this equation turns out to be 0 unless L and L dash don't equal. Okay? So effectively you've now gone down to 3 parameters, right? Because this representation here, this integral now just becomes